Okay, and now we are doing section .6, which has to do with functions and graphs and some geometry and business examples, just a couple things that I want to make sure that we have under our belt as we look forward to moving into actual chapter 1, which is going to have more calculus to it than algebra. So, example from geometry, something that hopefully you've seen somewhere along the way, is that you might have a situation where you know something about a rectangle in terms of how its sides are related to each other. So in this case, the longer side is twice the shorter side. So if that's the case, algebraically, we would express one of the sides as x and the other as 2x. And that would allow us then to come up with different expressions for different things like perimeter, area, that kind of thing. So the perimeter of this rectangle would be adding up all the sides, and that would be 6x. The area of this rectangle would be multiplying length times width, so that would be 2x squared. So algebraically speaking, we can write expressions for those things once we know, once we have a way to express the length and the width both in terms of x. And if the rectangle represents a kitchen countertop that we're constructing, and the material is $25 a square foot, we could then also write a cost function for that, because we know that the cost to make the countertop would be 25 times the area. And so the cost function would look like 50x squared. So if you tell how wide you want the countertop, then we could express how much it's going to cost, 50 times however wide it is squared. So algebraically setting these things up is just important. We're going to have word problems where this is sort of an assumed piece of knowledge. Example number 2, we could go 3 dimensions now, and we could have a box where we know that there's a square base that's made of copper, there's wooden sides, and a wooden top. If the copper is $25 a square foot and the wood is $2 a square foot, we could figure out a way to express the cost of those materials to make the box. But first we want to know, how do we express surface area? How do we express volume? So surface area is all the material that you need to make the box. That means you need to make the bottom of the box, whose area is x squared. The top of the box, whose area is also x squared. Bottom and bottom. Bottom and top. And you need to make 4 sides. So each of those sides is represented here. This one is x by h. This one is also x by h. The back one, if you can imagine it, is x by h. And the side is x by h. So surface area for this would be, I'd need an x squared and an x squared for the top and the bottom. And I need 4 sides, which each have an area of x each. And that's going to give me the surface area for this box. So the area of all the sides of it. The volume of a box is always length times width times height. You just multiply up all the dimensions. And in this case, that'd be x times h, which is x squared times h. So the cost of the material, in terms of the dimensions, that would be using the weighted amount. Because remember, they said the copper, which is the base of the box, is $21 a square foot, so that's pretty expensive. And all the rest is wood, and that was $2. So that was the rest of this box that I'm making. So what I'm going to do is look at my surface area formula, but go back a step and look at it, because this was the bottom of the box. this would be weighted $21 for every one of those square feet. And the wooden part would weight, the top of the box is 2x squared, and the sides of the box is 8xh, because we're multiplying them by 2 instead of 21. And that gives us a way to express how much it's going to cost us to make this box as soon as we know what x is. But I shouldn't have done that, because that's not just in terms of x, that's in terms of x and h. So the cost of the box, if we know what x is and we know what h is, would be written like this. So, business problem. We've got a manufacturer of toys who's got a fixed cost and a variable cost, which we've talked about previously. And if he's going to make 2,000 toys, that's going to look like all of his fixed costs will be spent because he went into business, and we're going to be charging $2 for every one of those 2,000 toys he makes, and that means that he's going to have $7,000 available to make 2,000 toys. To get an additional cost when he raises his production level, we don't have to worry about the fixed cost because we've already incurred that fixed cost just to go into business. We would need to spend $2 for each additional toy that he decided to make. So additional cost we don't incur fixed cost again. That's sort of water under the bridge. We've already paid. If I want to know how many toys he can make for $5,000, then I'm going to set it up backward, and I'm going to say 3,000 of that will be his fixed cost, but I now have to figure out, well, what's left from that fixed cost, and I'm going to have to divide whatever's left by 2, because that's how much each toy is going to cost, and then I'll know how many I can make. So I'm just working backward. So the $2,000 that he has to spend after his fixed cost will give him 1,000 toys that he can make. And finally, the idea of a profit function. We want to make sure we know what profit is. Profit is the money made after cost is taken out. So profit is your revenue minus your cost, because revenue is the amount of money that you pull in when you're doing your business. Cost is the amount of money it costs you to pull that money in, and profit is the difference. So in this case, the $10 a piece tells me that the revenue function is 10 times however many units he decides to sell. And we knew our cost function was 3,000 plus 2 times however many he decides to make. So our profit function will be 10x minus 3,000 plus 2x, which is going to end up being 8x minus 3,000 when we combine up our 10 and our negative 2. So revenue minus cost. This example number 4 here, try to zoom out a little, has a graph where we are planning for future growth, and we decide that we have production costs for one of our products that follows this cost function formula. So this is a little more complicated type of formula. X is still the number of units I decide to make, but the cost function is not as simple as a fixed cost plus a linear variable cost. But what I want to make sure that we're all comfortable with is how to read a function and function notation. So the fact that the point 16, 715.12 is on the graph, what that means is the cost to make 16 units is $715.12. So the X is the number of units, the cost is the cost, and they match together as an ordered pair. How can you use the coordinate of a point to help solve an equation? An equation like C of X equals 900 or Y equals C of 14. So you just want to know that if they told you C of X is 900, you would want to match Y equals 900 with the X value that you find there. So you would look at a Y value of 900, follow it over to try to find the X value that matches, and you could figure out a production level. So the X value that matches with that Y value is going to give you a production level. And then if you work backward, and you're trying to figure out C of 45, what does that mean? Then you're going to be going at the 45 on your x-axis up to the curve and back over to figure out a cost. So if you're given a Y value, you could follow it along and come down and get an X value that matches with it, a production level. If you're given an X value, you'll go up to the curve and over to the Y-axis to find the cost. So C of 45 will give you the cost for 45 units. Given an X, go up and get the Y. Given a Y, go over and down to get the X. And then last but not least, technology to approximate a minimum and a maximum value on a graph. That's something that you do on your graphing calculator. So I am going to leave that for class so that we can talk about it because I don't have my graphing calculator with me right now. But if you want to practice it, you want to make sure that you put this into your Y equals on your calculator. And after you have that in your Y equals, you want to go to second calc. And after you go to second calc, you'll have choices. And the choice you want to pick is, minimum and maximum, sorry, not a value. Second calc, and then max. And we can see right here that it looks like there's a maximum here. And the important thing to know on your calculator is after you go to second calc max, you want to give it some boundaries so that it knows sort of where you think the max is. So it's going to ask you to show it where you think you are when you're to the left of the maximum. So you're going to have a little arrow that's going up on your graph, and you're going to get to the point where you think you're to the left of the maximum, and then you're going to hit enter. And then it's going to ask you to get to the right of the maximum. So you're going to move to the right, and you're going to hit enter. And then you're going to hit enter one more time. And it will then find itself at the maximum and tell you what it believes the maximum is, and tell you the X value for the maximum also. It'll tell you the Y value and the X value for your maximum. And you can do the same with the min. Second calc min, get to the left, hit enter, get to the right, hit enter, and hit enter one more time. But we'll go over that in class just so that if you have a graphing calculator, we can make sure you're okay with that.